Hello, this is Michael Sulak, and this video is going to be about the geometric distribution, which sounds a little scary, but really isn't that bad. And for the geometric distribution, we're still going to be dealing with the same setup as a binomial distribution. So we have these independent Bernoulli trials, and we're still going to be counting something, but we're not going to be counting the total number of successes. We're going to be counting the total number of trials until we get the first success. So it's still a count, but it's a different type of count. So, for example, suppose we had a coin that wasn't fair and it had a probability of heads of 40%. And suppose we were looking at the outcome of heads as being a success. Then if we were to talk about the count of the total number of trials until we see our first success, that is a geometric count. And the outcome that corresponds to that count is seeing 3 tails and then a heads. We could call these 3 failures. And then our first success. So if the variable is the number of flips until we get our first heads, then we could refer to that as being a geometric random variable. And you'll notice that this is a different situation from a binomial because the number of trials is not fixed. You could get the first head on your very first flip, or you could get the first head on the 10th flip. That's pretty unlikely, but it's possible. So there is not a given number of trials. A binomial random variable would be something like the number of heads out of 7 flips, or the total number of heads out of 10 flips. And geometric calculations are actually slightly easier than binomial because there's fewer ways that they can happen. If we want to talk about the probability of getting 4 total trials, so kind of translating this into some symbols, the probability of our random variable x being 4, which is the probability of needing to see 4 flips until we get our first heads. To find that probability, we just need to multiply the probability of a failure times itself 3 times, times the probability of a head, and we get about 8.64%. So there is a formula for observing a given number of trials in total before you see the first success. If we're just calling the number of trials needed some number k, then what happens is we need 1 less than k failures, and then we need our 1 success. And you'll notice that we don't have to think about multiple ways that this event can happen because there's only one way it can happen. Whereas in the binomial distribution, there was a choose formula. There's no choose formula here. The calculation is quite a bit simpler. If you're talking about observing 6 total trials till the first success, then you know that had to be failure, 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 and then a success. There's no other way that could have happened. So here are some results for the expected value and the standard deviation of a geometric random variable. And you'll notice the value p occurring fairly frequently, and we're using that as the probability of seeing a success on a given one of our Bernoulli trials. So suppose a coin has a 25% chance of heads. We're going to count the number of trials until we see our first heads. Well, the expected number of times we're going to have to flip this coin, the expected value of x, is 1 over the probability of success, which is a fairly intuitive result, I think, that if a coin has a 25% chance to land on heads, then on average you expect to need to flip it 4 times in order to obtain your first heads. The smaller the probability of a success, the more trials you expect until you get your first success. So let's do an example. Suppose that it's just given that 91% of all email is spam, and we're going to assume, and we need this in order to do the calculations with the geometric distribution, that emails arrive independently. And so we might ask a few questions. How many emails would we expect to check before finding one that isn't spam? And this before can be a little bit confusing. It might be better to refer to this as the total amount of emails that we need to see one that isn't spam. So all of these questions that are being asked here are about a variable that has a geometric distribution. And it's always good to think about what a success is. A success is an email that isn't spam. And always good to think about what the probability of a success is. So that's finding a message that isn't spam. So if 91% of all email is spam, then 9% of email isn't spam. So that's our probability of a success. So if we're asked how many emails should we expect to check, we'll just need to take 1 over the probability of a success. So doing that calculation, it's a little bit more than 11 emails. Here's another question. What's the probability that the fourth message is the first one that isn't spam? So what does that mean? Small error down here. That means there were 3 failures and then a success. The probability that our count is 4 is the same as the probability of seeing 3 Fs and then an S. So we need the probability of an F, which is what's happening in the formula here, 1 minus P, times the number of failures, which is 3. And then we need the probability of a success, which is P. And there's always just one of those. So the probability that we have to look at 4 messages to see one that isn't spam is about 6.78%. So those exactly equal to probabilities are relatively straightforward, but what makes it slightly more complicated is if you want to know the probability of events that include more than one possible outcome. Like just using generic terms like what's the probability of seeing the first success any time before the 5th trial. What's harder about that is that sometime before the 5th trial means that it could have been on the 1st trial, it could have been on the 2nd trial, it could have been on the 3rd trial. There's several ways that this could happen. So using our notation we've been saying, there are 4 ways that correspond to this particular event: getting the success immediately, or getting it on the 2nd trial, up to getting it on the 4th trial. You'll notice that this says before the 5th trial. That means at most it happens at 4. So we could find this probability by adding up the individual probabilities of each of these events. They're all mutually exclusive. There's no probability of counting twice, no danger of that. And that's not the end of the world. But it will certainly be easier if we use a computer at this point. So we're going to use R to find these slightly more complicated at least or at most probabilities. And using R, we have to just look at a problem in a slightly different way than the total number of outcomes. For example, if we were talking about needing 4 total trials in order to see our first success, we would call this event X equaling 4, where X is the total number of trials. But to use R, the count that R uses in all of its functions, I'm not totally sure why, but it is what happens, is that R wants to know not the total number of trials, but R is going to want to know just the number of failures that you needed. So if you saw 4 total trials in R, what you're going to say is that's the same thing as seeing 3 failures before we get the success. So we just need to modify the count slightly. And instead of using the total number of trials, we're going to use the number of failures, which is always going to be 1 less than the number of trials. It's the same event. We're describing the same thing. We're just counting a slightly different characteristic. So the by hand formula would apply to using the total number of trials, and then in R, we're going to change it to the number of failures. So in order to keep that hopefully slightly more clear, instead of using an X for the number of failures, I'm going to use the letter Y. So Y is just going to be one less than the total number of trials. For that example we looked at previously, X was 4, but then the number of failures is just one less than that, 3. If you want to find the probability of getting exactly a certain number of failures before the first success, you're going to use dgeom in R. The D stands for density. The geom is for geometric. And you have to give it 2 arguments. The first one is what I would call the specific value. So if you want to get the probability of needing 2 failures, Y would be 2. If you need the probability of seeing 10 failures before the first success, Y would be 10. And then this P is just the probability of success. Again, these are the argument names. You can leave those out if you like, as long as you use them in that particular order. Let's look at examples using this. So say we're doing the same email example where we had the probability where our success was the email not spam, and the probability of a success was 0.09. So if we want to know the probability that the 10th email is the first non-spam without another error. That's the probability of seeing 9 failures and then a success. So it's the probability of failure to the 9th times the probability of a success, which gives us about 3.9%. If we wanted to verify this with R, we're going to use dgeom, and we're going to use the number of failures, not the total number of successes. So we're going to use the number 9 in our function. We'll use 9 failures here for the first argument, and then 9%, 0.09 for our probability of a success. And we're going to get the same value, which is good. We're expecting that. It's always nice to do it in both ways and see that they end up being the same. We can be pleased with that. Okay. When R is especially helpful is if you want to find events, like we said earlier, that are just more complicated, less than or equal to events. To find the probability of seeing less than or equal to a certain number of failures, we're going to use pgeom in R instead of D. So the dgeom, it's good to pay attention that this always includes the value and everything less than the value. So if you ever wanted to do something like find the probability of seeing, less than 6 failures, that's going to be the probability of seeing at most 5 failures. You would use 5 as your argument in pgeom. So let's look at an example. So what's the probability that we need a maximum of 10 emails in order to see our first non-spam message? So we could do this the long and awful way by finding 10 geometric probabilities and adding all those, which in R isn't actually that bad, or we could also use that pgeom function and say, okay, so a maximum of 10 emails means at most, so this is 10 total emails. That means that at most we would need to see 9 failures. And so we're going to put 9 into pgeom. So the probability of seeing at most 9 failures is calculated by R to be about 61.05%. So using the wording of the original question, there's about that much of a chance that the first non-spam message will occur sometime within those emails. So, it's within 10. This is like the first success is within the first 10 trials. So that is an at most question. So dgeom and pgeom are the 2 things that you need to be able to use to find any geometric calculation that you'd like. Let's do another example with different data. So suppose we have a group of 1,000 people, and in those people, 5% have type AB blood. If this question says, on average, how many donors do we have to check to find someone with type AB blood? So type AB blood is our success for this problem. Always good to start out by paying attention to that, which means that the probability of a success, which is P, is 5%. And we're going to be using the decimal equivalent 0.05. So this question is asking for the expected value. Expected value is an average. The expected value of this variable, the number of donors we need to check, and then, so this is the total number of donors here, is 1 over 0.05 is 20 donors. And again, this is a total amount. So let's go on. Okay, so what is the probability that there is a type AB donor among the first 3 people checked? We're talking about choosing 3 people, and presumably we're doing this without replacement, which is not going to be perfectly independent because, say, your first person was type AB, that means you have 1 less person with type AB blood in your group to choose for the second person. But when you have a big enough sample, 1,000, even though it's not perfectly independent, it's relatively close. So we're just going to assume that they are exactly independent. Again, all of this is just a model. It's not going to be exactly what happens if you do this in the real world, but the idea is that hopefully it's close. So the probability that we get the first donor among the first 3 people is the same thing as saying we need a maximum of 3 total trials, which means that we need a maximum of 2 failures. So 2 is going to be what we put into our function, our pgeom function, because again, we're using a maximum, not exactly equal to. So we're going to be finding 0.142 about as our answer, which we could say that, hey, there is about a 14.3% chance that this event will happen. So the next thing we'll look at is what's the probability of at least 10 people. So this is a different type of question until the first AB donor. So at least 10 is the probability that our total number is going to be greater than or equal to 10. And there are a lot of ways this could happen. You could have to check 10 people or 11 people or 12 people or 13. And actually, the probabilities get very low, but there are technically an infinite number of people you might have to check. So what we're going to do is figure out what's the opposite event, the complement of the event we're trying to find the probability of. And we're going to find the probability of the complement. And then we're going to use the complement rule, which is the sum of their probabilities has to equal 1. So if I'm calling this event A, where I have at least 10 people, then everything else is a complement. Well, what is everything else? Well, it's all the numbers before 10. So the complement of this event is going to be that X is less than or equal to 9. And again, what I'm talking about here when I use X is that this is the total number of people that we need to check in order to see the first person. I could rephrase that slightly and say the complement is that it's the event where the first AB donor is somewhere within those 9 people. That's the same thing as saying that it's at most 9, which is the same thing as saying that it's less than or equal to 9. So now I know that that means what this event is talking about is saying that I could have seen at most the 9th outcome being a success. This is the latest, if you want to use that term, success that's included in this event. So what does that mean in terms of the number of failures? Is that the maximum number of failures we would see would be 8. The complement of the answer we're trying to find is seeing at most 8 failures. So I could describe that as being the probability that the number of failures is less than or equal to 8. So to find the answer to our question, we're going to do 1 minus the complement, which is 1 minus seeing at most 8 failures. So we're going to do 1 minus pgeom of 8 and get about 63%. When you want to do at least questions, one way to do it is to find the complement and use the complement rule. Then the last one that we'll look at is what about we want to have between two certain numbers. So what's the probability that we have to check between 10 and 20 people? So inclusive means it counts both of those until we get the first type AB donor. That's the probability that X is at most 20 and at least 10. It could be 10 or 11 or 12 or 13 or 14 or etc. up until 20. In order to answer this in R, we're going to translate that to failures. So the failures are one less than the total number of outcomes. So it's the probability that Y is within one less for each of those endpoints. Here's two ways you can do this. You could do dgeom to find all the possible probabilities that Y is all the numbers in this interval and add all those. I'm going to do this all in one step. So when I do that, I get 27.17% about. So that's the answer to this question. Chance that we have to check a total of 10 to 20 people. And then another way you could do that if you want to is we're going to use pgeom, and we're going to find the interval by finding the probability that's less than or equal to 19, but that's too much. And then we're going to subtract off how much too much that is. So when we do it that way, we get the same value, which is what we expect. And if it's a little freaky to you that this ends up being an 8, sometimes it's helpful for me to make a little picture of possible values of Y. And sometimes I'll kind of just be thinking about the distribution here. So, the possible values of Y here are starting at 0 and going up, and I'm going to skip some stuff. So eventually they could be like 7 or 8 or 9 or 10. So again, I'm looking at, this is the number of failures. So they could be 10 or they could be 11 or 12 or etc. up until, let's look at 19 or 20. So the answer to the question was, what's the probability of seeing all the values between 9 and 19? We want to sum these. What we're going to do is say that the sum of those is going to be equal to, from 19 all the way down, that's what doing that pgeom the first time, finding the probability that Y is less than or equal to 19. And then we have too much. How much too much do we have? You'll notice that 8 is the number that we want to subtract. We want to get rid of all of these areas. This is how much extra we have. So the probability that Y is within the interval of 19 to 9 is the probability that it's within the interval of 0 to 19, but then minus the probability that it's within the interval of 0 to 8. And then we'll end up with just what's left here, which is what we want. This is what's happening in this calculation in R. We're doing that. And you might say that was a lot, and I kind of agree. It might be easier, honestly, to use the dgeom method, where you're just going to say, I want all the values from 9 to 19 and add all those. Or you could do it both ways and see that they match. So this is Michael Sulak signing off. Thanks for watching, and take it easy.